Hi, I'm Cliff Elwell from the Physical Characterizations of Building Group at UCL Energy Institute, presenting today with work from Francis Hollick and Jez Wingfield. And what I'm going to talk about today is thermal performance estimation of homes and what the requirements might be for these, how the estimated heat transfer coefficient or HTC might vary and why, and then the factors affecting empirical estimates of the heat transfer coefficient. And I'm particularly going to focus on a really simple example of temperature measurement using a basic model. So first, what are the accuracy requirements of an HTC estimate? Well, I've put in a whole load of use cases here, and we can see that the method of HTC estimate depends on what you're trying to achieve and the amount of disruption and cost that you're prepared to accommodate to achieve the required accuracy and how repeatable and reproducible that should be. So taking just a few examples of these, if you wanted to assess new build performance, perhaps you might like to do that before people have moved in to assess the performance gap versus design, and you might use an unoccupied test for that. Whereas if you're looking at the improvement due to a retrofit, it's likely that there might be occupants in there, and you might only be looking for a difference. You might not be looking for an absolute HTC, but rather the difference between it. Whereas if you want to estimate the energy or cost savings associated with installing a retrofit measure, so you might be thinking about the metered energy savings or pay as you save, you might not want to estimate the HTC alone. You might be wanting simply to use a machine learning or an AI method that aren't necessarily simple, but a simple approach. So first, I wanted to highlight what we all know, which is that HTC isn't a constant. So despite the fact that HTC is defined variously, we're going to use the ISO standard here. And this includes in particular infiltration and ventilation openings. So this leads to, in part, to two significant reasons why HTC is going to vary over time. The first one being seasonal variation, which we'd expect because of differences in ventilation. There's a really obvious cause here where internal doors may be opened differently in the winter from the summer, or in the shoulder seasons, or during different periods of occupation, different occupants in general. And of course, this leads to different airflows through the home, and then slightly separately, you've got airflow through cavities, through leaks in the structure, through the intended ventilation, and so on. And that all changes the HTC. The second reason, of course, is that HTC just varies over time due to, for example, cracks developing and degradation of the fabric, but also just changes to the fabric that might be there for aesthetic, structural, or energy performance reasons. So jumping right into how you estimate HTC, looking at unoccupied homes, I've got some kit here for a co-heating test, and that's the standard I would say that we're using at the moment. It's disruptive, it's time consuming, but there are faster methods that are available and being developed. But these methods are never perfect. And there are a few reasons for that, and here's some examples. So, of course, the analysis failing to capture the physical effects, such as not accounting for solar gains perfectly or the ground temperature. Big question here as to what you're trying to achieve by this. Are you trying to achieve some the performance of a home in a state in which it could never be used or would never be used by an occupant, or do you actually want to represent the use of a home much better, for example, without big fans blowing? You might, we certainly need to worry about the repeatability and the reproducibility to get consistency between different testers. Always going to worry about where the equipment is, its accuracy and precision. And finally, big issue with guarding, so setting adjacent properties to the same temperature to get the most accurate results. But then when we move to occupied homes, we've got all those problems, but on top of that, we've got many more problems as well. And that's for practical and other reasons, where practical reasons include things like the limitations on the equipment size and quantities and so on because of the disruption to occupants. major issues with behaviour in terms of understanding what ventilation might be going on, hot water use, energy storage, energy use outside the home. Perhaps they've got an electric vehicle, and how our models can cope with that and how these things are measured. We need to think about the performance of the heating systems that's used, what we consider as useful heat, what's just a loss. We need to think about the metabolic gains, particularly in high efficiency homes, on-site generation, and solar gains are no longer simply dealt with the curtains or blinds in one position. They're now used dynamically, and many more impacts besides. And so what I wanted to do was take a really simple model and illustrate how temperature variation can impact on an estimated HDC. Deliberately, it's a simple model shown at the bottom here, with HDC estimated by multiple linear regression. It's simple to make sure that we can see the effect as clearly as possible, and it's investigating the impact of where you measure the temperature. So 30 houses, temperatures measured in lots of spaces, and we compare the HDC estimated from an area weighted mean across the whole property to that where we just take a bedroom temperature or just take a living room temperature. And on average, they compare pretty well, 2 to 5% difference, significant difference, but relatively small. However, the variation across properties can be huge, where you've got an up to 37% difference between the HDC estimated from the living room temperature alone to the area weighted mean, which is highly problematic and something that needs to be accounted for in our methods, particularly because the spatial heating patterns will then affect the HDC. Not only is it occupant dependent, but it might change for the same occupant when, for example, they decide they're going to work from home, as we all have, and we perhaps end up heating more of the home than we did before for a home office. And the second form of HDC variation due to temperatures that I wanted to talk about is party elements, where there's a problem here with simple models and measurement, that you can't tell the difference between the fabric and the party walls, the external fabric and the party walls, and the party wall heat loss or gains can bias the HDC estimate either up or down. Now, obviously, there's a lower temperature difference between properties than two outside, but there's also a higher U value across a party wall, and there's always the potential for party wall bypasses as well that we have to be alert to. So what we've looked at here is 3 nominally identical houses and estimated the HDC using another simple method, although this time we've included an estimate for the hot water usage because we had heat metering. And first thing to note is that house 120 is cold compared to the others, and the result of this is in the estimate of the HDC for plot 120 is very low. It's very low because there's actually a lot of gains into that home through the walls from 119 and probably 121 as well, where they're providing free heat, and this pushes up the losses for plot 119 to give a higher estimated HDC, which is still higher than the design. When we account for the real HDC as well, plot 118 and 120 had hot water usage in line with expectations, but 119 had huge hot water use, and this pushes the HDC up again. So we're seeing again a really big impact potentially of that party wall heat loss. There might be some other factors as well if we were to look at the house forensically. Well, I wanted to give a little bit of hope here because it sounds like empirical estimates of HDC are all bad. And so I've just got 2 studies here that I think that show the advantages that they can have. The first is a nice study by Leeds Beckett that estimated that 36 to 64% of EPCs contain errors, and that those are typically around 4 points. Well, what is 4 points? Well, if you take a terraced house built to 1995 standards, If you take 25% off the HTC, that gives you 5 extra points on the EPC rating. But if you add 25% to the HTC, you lose 4 points. So quite significant changes to the HTC associated with that 4-point difference. Second paper is in some ways a little bit like a follow-on from the mystery shopper exercise that we're all familiar with, where we at UCL analysed the EPC ratings of a repeat measurement, often after a number of years, following an initial EPC with rating 40. Now, the first thing to note is you don't expect to see any EPCs below the 40. It's highly unlikely that there would have been changes made that made the thermal efficiency significantly worse. We do know that there's a really big improvement in EPC rating, and HTC is likely to underpin that. It's very strong in the calculations, and we particularly note that there's a big jump in the EPC rating between E and D, where suddenly a lot of properties are just squeezing in within the D boundary. That's not the kind of characteristics that you expect to see from a distribution. So that's some cause for concern as to the methods used and how independent they are. So to conclude, the best measure of thermal performance depends on the application, and we shouldn't be aiming to use one method for everything. The HTC is variable, and we always have to be bearing that in mind. And there are a huge number of things that can impact on an empirical estimate of HTC. And for occupied properties, this is challenging. However, we need to think about what we're really trying to achieve from this, and whether we are interested in the occupied state or the unoccupied state, and how transferable we expect the HTC rating measurement to be for different occupants. Using a simple example of a basic model, we can see how important temperature estimation is, both within a property and across the party walls. And I think the key thing here is that if we're going to see a wide-scale rollout of methods to have empirical measures of thermal performance of properties, we have to demonstrate the robustness of those methods to all these factors and many more as well, in order to support that uptake and build confidence. Thank you.